right. So yeah, I basically want to start, with a very general kind of overview. And if we go all the way back to, Satoshi Nakamoto himself or herself or themselves, whatever it is, um, the main invention there was that, he invented a mechanism to basically guarantee security, not just by means of cryptographic primitives, but by means of a game. Like, with cryptographic protocols or primitives, the name of the game is always proving that, like, no matter your computational power or whatever, the difficulty of, breaking the thing is always very, very high, complexity speaking, and it's all a game of that kind of assurances. And instead, with the invention of, the blockchain and Nakamoto consensus, the idea was, well, like, breaking the blockchain is not that hard. The problem is just that it's crazily non-convenient to do so. Like, you have to spend basically a lot of money in computation, way more than, what you will be able to get. And at that point, he invented crypto economics. Basically, he invented this idea of guaranteeing properties of protocols by fine-tuning the right systems of incentives. So this kind of, initial idea has obviously developed in many ways over the years. And I think in the last couple of years, probably, we are starting to see how this idea is always also taking hold in the field of security auditing. So what I mean is that if we look at, a lot of auditing firms, basically the kind of audit work that is done for, like, smart contracts and protocols is about making sure that the code does what it should do. And obviously, like, every firm has, their own tools to do that. Some of them use theorem provers, some of them use ad hoc formal languages and stuff like that. But in the field of crypto economics, as the name says, that there's crypto and there is economics, there are also a bunch of things that are at the fringe, at the seams between the interplay of mechanism design and cryptography or, coding. So in the last years, we've seen a few groups, collective firms, whatever we want to call them, that expanded in a way the scope of what it means to audit something by developing tools to stress test the mechanism itself. Personally, I am from 20 Squares, that is a company that focuses exactly on this. So the kind of auditing we do is not, code auditing. We will not make sure that your smart contract doesn't have a reentrancy attack vulnerability, for instance. What we do is basically making sure that your specification and the mechanism you design doesn't have any game theoretic vulnerability. That means that there isn't a game theoretic incentive to actually, misbehave or operate the protocol in a way that is not the one that the original designer intended. So how do we do this? Well, what we do is we use our custom software which is publicly available, by the way, which we call informally open games. The formal name of this software would be compositional game theory. But basically, the main idea is that this is a software that allows you to design mechanisms. Now, what do I mean by that? So in traditional game theory, you instantiate a game by basically giving some rules, some possible strategies that each player can play, and then you study equilibrium and see what happens and stuff like that. In compositional game theory, the idea is that games are thought of as open processes. So a game is basically a process that observes something, inputs something in the context it's in, gets something back from the context and uses it to calculate the payoff. I will show you a demo of all this in a second. But basically, the point is that, there is this formal theory of open games that my partners at 20 Squares have been developing for the last 8 years or so, which basically guarantees you that if you compose 2 open games, what you get is always an open game. So that means that the composition is semantically meaningful. When you compose 2 apples, you always get, an apple, basically. This seems to be not that important, but it's actually crucial for a simple reason, that when you try to, implement a mechanism in a system that doesn't have this kind of semantic safety, semantic compositionality, what can happen is that you compose 2 things in a way that seems to make sense, and the semantics, like your engine doesn't complain, but what you get is something that has no game theoretic meaning whatsoever. So you are composing 2 mechanisms in a way that, in the end you get some code that does something, but that code does not represent a meaningful mechanism in a precise formal sense. In our framework, this is basically prevented. We have a type checker that will tell you, hey, what you're trying to do makes no sense whatsoever. Think again. And this allows us to, be very fast in prototyping things. Because as I said, for us, a game is a process. It's basically a function, and I can plug it in different contexts. And so this allows us to prototype and model, for instance, a specification while the specification is still evolving. So it happened multiple times that, we were speaking with our client, and they had some ideas, they had some code already, but everything was a bit in a state of flux. This is a pretty frustrating time to operate for an auditor, because like you do a lot of work and then your client decides to change everything. And okay, maybe they pay you by the hour or something, so it's not a problem that you worked for nothing, but it still feels very frustrating because maybe you have to turn your whole formalization upside down to, keep auditing. Basically, with traditional algorithmic game theory suits, these would be immensely hard to do. It would be because they tend to be very monolithic. So following the development of the specification and the code with a game theoretic modeling would be very hard. In our framework is instead quite flexible and easy. So this said, I will try to share my screen. Let's see if it works. Share. Okay, so can you see this screen here? There should be some code.
Yep.
Okay, is it big enough, or do you want me to make the font bigger?
A tiny bit bigger would be best.
Okay, let's try it. How about now?
Perfect.
Okay. Okay, so now I'll show you an example of how this thing works. So this is some research project that we did for Flashbots, basically. And I like to present this because it's quite simple. So it allows you to understand how this game theoretic modeling / auditing works. So, okay, first of all, I'll show you the main ingredient of open games, that is this thing here. This thing is a game. Game name will be the name of your game. You can feed some variables to this name. I'll come to this in a second. Basically, we consider these variables as exogenous parameters, which means they are parameters that are not directly in your model. I'll get to that in a second. Now here we have the game itself. So there is some inputs. What did I do? Okay. There are some inputs here. The inputs are basically the kind of stuff that the game can observe from the outside world. There is some outputs. This is what the game does to the outside world. And you can imagine inputs and outputs going from the past to the future. You receive an input, you output an output. Then you have returns and feedback. And you have to imagine returns and feedback going the other way around, from the future to the past. So returns are basically the consequences of your actions. If you do, if you output S, something of type S, the context will return you something of type T. And you yourself may have to return something to the past, and that's what this feedback is for. So to give you an example of this, imagine that you are placing a bet at a casino, right? So you go to the croupier and you say, okay, I'm seeing these cards. This would be my input. I'm taking an action. Those would be my output. And what I get is a payoff. It's basically, you know, the result of my plays. Okay, I'm going to play this card. The return is telling you how much I made, or you know, how much did I lose. Now, my return would be the casino's feedback. Right? The idea is that what I'm being paid or what I'm losing is being fed to me by the counterparty, by, in this case, the feedback wire of the casino. So we have a way to represent these things graphically as boxes. So just to give you an example, let me try to open this twice. Yeah, does it work? Second, open preview. Okay. So I have this game here. And here I have the analogous of the code. So by the way, I still have to explain what's happening inside these delimiters. So in here, I have a big box. This is the big game. We see that it has two inputs, A and A prime. It has one output, S. It has two returns, T and T prime, and it has one feedback wire, B. Okay. Now, inside this box, I want to fill it with something else. So in here, I am placing two subgames. Now you see that this subgame, I want to say that this subgame here is taking A prime as input. So I just put A prime here. And basically this open game DSL is automatically, you know, piping this A prime wire into the port of subgame 1. Similarly, subgame 2 is taking A as an input, but it's also taking an X. This X is an output of the first game. So you see now we have an inside wire, this X here, that is completely unknown to the outside world. And it's a completely internal wire, basically. Then subgame 2 spits out an S. Subgame 1 spits out an X, as we said, that goes to subgame 2. And basically, if you look at all the wiring here, you can see that you can use this thing to basically make very complex diagrams, very, very complex nesting and combinations of games. Now, aside of, like, so in this basic format here, what can I put within these delimiters here? Well, as I said, we have inputs, feedback, outputs, and operations that are duplicated inside and outside, and this is what allows me to do the wiring. But then inside, I also have this operation box here, this operation field. What did I do? Okay, so this operation thing here is basically telling me what the game itself does. So there are various possibilities for this operation. Basically, it could be a game itself, like basically in this case, operation is sub game 1. It could be a function. I'm trying to find, yeah, it could be a function. A function is just something that transforms some input in some output. It could be a stochastic distribution, which we use it to implement draws from nature. So we say, okay, I don't know, if we want to set up a game where a given actor has a private valuation of how much something is worth, and we want to assign this valuation randomly, we can just, use a stochastic distribution. Or every time you have to implement like coin flips or this kind of stuff. Or it could be a strategic choice. So what is a strategic choice? A strategic choice is the core of game theory. It would be a function parameterized over a set of possible strategies. So the idea is that a strategy in this setup is something that says, if you observe A, then do B. That would be your strategy. Providing this thing would be a strategy. Moreover, we have another operation that is called branching, and branching is useful to implement situations where, depending on what is going to happen now, you may end up playing 2 different games. So I'll show you an example of this in a second. So now I think we can jump into some models that I can show you. And we start with the most famous model in all game theory, that is prisoner dilemma. So how does it work? Well, first of all, we define, by the way, the underlying language of this engine is Haskell. So we are basically going to write some Haskell, and then we are going to fill the game theoretic model with these Haskell functions. So the first thing we say, okay, we define a possible action in prisoner's dilemma that is either you cooperate or you defect. And then we implement a payoff matrix. So what does the payoff matrix does? Well, it takes 2 actions that would be the actions of both players, and it returns a couple of payoffs. So you see that in this case, if both players cooperate, they get 2 each. If one cooperates and the other defect, the cooperating one basically gets screwed and the other one gets a 3. Vice versa, this is the specular situation. And if they both defect, they get 1 each. Okay. So now that we have this very, very simple thing, we can implement the basic prisoner dilemma. So we do it this way. First of all, the prisoner dilemma is a closed game. So what I mean by that is that when the game is complete, like when we consider the prisoner dilemma as a unique thing, it has no inputs and it has no output, because there is no context outside of prisoner dilemma. What is inside the game? Well, we have 2 players, Alice and Bob. And what do these players do? They do not observe anything and do not return anything to the past. That's because in prisoner's dilemma, you don't have any prior observation, right? You just have to play and hope for the best. they have basically an operation that we call dependent decision, that is, basically saying, okay, this is the space of things that Alice can do. Alice can either choose to cooperate or can choose to defect, and that's it. Same thing, Bob. Bob can either choose to cooperate or to defect. And basically, the result of this choice is being output as a decision. So we have decision Alice here and decision Bob here. Now, both these players receive a payoff that is the consequence of their decision. Since this function returns a couple of payoffs, here what we are doing is Alice will take the first component of this tuple and Bob will take the second. Now, in here we have the prisoner dilemma payoff matrix that basically observes the decisions of Alice and Bob and outputs the payoff tuple. In the Open Games engine, there is this thing that is basically a silent wire that we implemented for convenience, so that you can directly feed the payoff tuple as a return to previous players. So you see that this is in very stark contrast with traditional game theory stuff, because in this version of Prisoner Dilemma, both Alice, Bob, and the payoff matrix are games by themselves. They exist by themselves. I can literally copy paste this in some other piece of code. We'll do it in a second. And that's, a game that I can reuse. So basically now the composition of these three games give me a resulting games with no wires whatsoever, so a box. And that is the equivalent of a traditional game in traditional game theory, implemented monolithically. Okay, so what can I do with this thing? Well, I can do a lot of things. First of all, I'm firing up a REPL that is basically an interactive console that I can use when I do Haskell stuff. Now, this is the game here. And I can actually ask, what is the type of this game? So I do type, Prisoner's Dilemma game. And it returns me this monster here. Maybe I can try to a little bit bigger. Oh, come on. Oh, okay. So this is what a prisoner dilemma is. It's basically just a big function that takes a bit of things. It takes strategies that are represented in this way. And in this case, yeah, basically returns nothing. So how do I use this thing? Well, I have to supply some strategies to this thing. So we defined another file called strategies.hs. And for the prisoner dilemma, we define two basic strategies. One is cooperate and one is defect. The cooperate strategy just chooses cooperate, and the defect strategy just chooses defect. The reason why we have to instantiate it in this complicated way by saying like Kleisli, stochastic, blah, 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 is because our games are natively Bayesian, which means that they allow for probabilistic reasoning and probabilistic strategies. So you can say, actually cooperate 50% of the times and defect 50% of the times, for instance. In this case, we're saying, no, play cooperate with certainty or play defect with certainty. Now, in this game here, where is it? Okay, sorry. So in this game here, we have two players that have strategic content. We have two dependent decisions. The payoff matrix has no strategic content because it's just a function. Forward function means that as an operation, we are just giving a function. So this thing has no strategic choice whatsoever. But we have, overall, two strategic decisions that we have to supply. How do we supply them? Well, we supply them as a tuple. So strategy tuple cooperate is cooperate, and strategy tuple defect is defect. Sorry, not a tuple, a list. Just confusion on my part. Okay, so how do we use this thing now? Well, basically, you have this function that is called isEquilibrium. IsEquilibrium is basically a function that checks, given a game and given a strategy, a strategic profile, if there are profitable deviations for players. So I can do, isEquilibrium prisoner's dilemma, strategy tuple defect. And in this case, it says, no, actually, that's fine. Strategies are in equilibrium. So what this means is that, there is no better solutions for these couple of players. They can't do anything more. But if I do cooperate, for instance, now it says, no, strategies are not in equilibrium, considering the following profitable deviation. So player Bob, if at the moment it's getting a payoff of 2, but if it defects, it will boost its payoff to 3. And similarly, Alice can, defect and boost her payoff to 3, and so profits more, basically. What isEquilibrium is doing under the hood is just, exploring the action space for your strategy. So in this case, it's very easy because you only have 2 possibilities, cooperate and defect, and it's calculating, the payoffs for each decision, and it's basically telling you if whatever you provided was the optimal move or not. In this case, we are implementing a very simple mesh equilibrium that is totally okay for games that are non-cooperative, but we can also use other notions of equilibrium where basically there is some form of cooperation. Okay, so now we had this very simple game that everyone knows. So why did Flashbots want us to do this? Not for this, obviously, that they really knew perfectly how Prisoner Dilemma works, but they wanted to experiment with versions of Prisoner's Dilemma with commitment devices. So what is the idea here? The idea here is the following. We have a Prisoner's Dilemma where Alice can provide a commitment device. What is a commitment device in this case? A commitment device, we modeled it just as a function that takes the strategic decision of Bob and output a strategic decision for Alice. So basically, Alice is saying, hey, I'm not deciding anything. I'm putting this box here, and whatever you do, this box will take the strategic decision for me. So Alice's commitment will be a function that, as I said, takes Bob's decision and outputs Alice's decision. Since we didn't want to fix things too soon, we are passing this function as what we call an exogenous parameter. What it means is that, this Alice commitment function can be provided later on in the modeling. So indeed, if I do now type Prisoner's Dilemma Bob under commitment, I see that the type begins with this line here. It begins with this line here, action, prisoner dilemma, action, prisoner dilemma. So what we see is that now the type of this game is a function that takes a function in input. This is exactly the type signature of this thing. And then, it takes all the strategic stuff that you have to provide to a game, and then nothing, then it's completed. So Okay, now what we do is basically the same. We just replace Alice with this game here. This game is basically the one we had before. We reutilized that. We have the usual, payoff matrix exactly as before. And now there is basically a problem. The problem is that since Alice is not a strategic player at the moment, because Alice is just a function that reacts to whatever Bob does, we have to manually add the payoff, one of the two payoffs that the prisoner dilemma payoff matrix spits out to the player Alice. Okay, so how do we define this Alice commitment? It's here in the strategies, and it's very simple. We say, okay, the commitment strategy is if the action I observe is cooperate, then I cooperate. If it's something else, then I defect. So Alice now is effectively saying, look, Bob, I'm deploying a smart contract that basically will observe whatever you do and will react accordingly. And I basically delegate whatever strategic decision I may take to this commitment. This has very interesting consequences that we can see here. So if I take this and I run it, so what I'm doing is I'm giving the conditional cooperate exogenous parameter. So this is the commitment device that Alice uses. And what is the strategy for Bob? Well, the strategy for Bob is cooperate strategy. And now we see that things changed because now Bob makes basically more money by cooperating. And indeed, if now I do this, let's try to do this on the fly. Let's call this Bob strategy defect. And here I put defect strategy. I save, and here I hit this to reload the thing. Okay. Now, if I say defect, say, yeah, strategies are not in equilibrium now. Considering the following profitable deviation, if Bob cooperated, he would get payoff 2.0. Instead, now he's defecting and Bob is getting payoff 1.0. Why so? Because Bob now knows beforehand what Alice will do when he plays, right? So basically, there is no reason to play defeat in this, defect in this case, because you know that if you do, the other player will defect. Okay. So this is very nice. And we have, these, we said, okay, cool. Commitment devices solve everything, right? Now we have a way to turn prisoner dilemma into something where people are forced to cooperate. Well, not so quick. So by the way, this is a research that is based on a research by Xingyuan Sun from Flashbots. And, we implemented this research that he did on with pen and paper in a formal model. So what can happen now? Okay, first of all, yeah, let's go here first. Okay, so now basically what happens is the following. Alice doesn't just submit the same commitment device. Alice now submits a commitment device that is extortive. So what does it mean is, Alice says, if you cooperate, but you also transfer me one of your payoff or more, then I cooperate. Otherwise, I defect. So what it means that, what Alice is doing is the following. If we both defect, we get one each. If we both cooperate, we get 2 each. But now Alice is exploiting her commitment device by saying, we both cooperate, but you give me 1 minus epsilon. So Alice is basically setting up the game in a way so that for Bob is epsilon more convenient to cooperate than the fact. But, you know, in the end, Bob will still be screwed, basically, because he's getting 1 plus epsilon and he's giving all his, you know, gains to Alice. So basically, again, Bob can either cooperate or defect. And, you know, it takes a decision. Now what happens is that Bob has also another game. Now Bob observes his own decision, and basically this is implemented in the strategies. The idea is that Bob says, if I cooperated, I will also transfer some money to Alice. And this is what Bob can decide to transfer: 0, 1, 2, or 3. Okay. Now you see that the payoffs that Bob gets is the payoff Bob that is returned by the prisoner dilemma matrix minus the amount that Bob transferred to Alice. Now again, Alice uses a commitment device that is just like looking at if Bob cooperates or not and how much Bob transferred to her account, and outputs a decision. And yeah, that's basically it. Again, the payoff of Alice would be basically the matrix payoff plus whatever Alice gets from this. Okay, so if I run this game, that should be here. We see that we have that everything is in equilibrium. And again, what is that we used here? Well, the strategic tuple that we used should be here. So yeah, so basically Bob chooses to cooperate, and Bob chooses to transfer. Let me see. Yeah, and Bob chooses to what is it? 1 second. Condition cooperate. Yeah. Bob strategy. Yeah, Bob transfer strategy is here. So Bob decides first to cooperate. We have to basically provide a strategic decision for each sub game in the game, right? So that is here. So first of all, Bob decides to cooperate, and then Bob needs to have some transfer strategy. The transfer strategy says, I observe myself. Remember, Bob observes its own decision. So if Bob decided to cooperate, it will deterministically transfer 1 to Alice. Otherwise, if it played defect, it will transfer nothing. So yeah, and this is an equilibrium strategy. And we can see that if instead we pump it up to 2, then it doesn't work anymore, because basically now Bob's payoff is 0, but if he gave 1, his payoff would be 1. If instead we play 0, let's suppose that Bob wants to cooperate, but doesn't want to transfer money to Alice. Well, in this case, again, we don't have an equilibrium because the current payoff for Bob is 0. Why? Because Bob is cooperating. But we know that Alice says, if you don't give me at least 1, I will defect. So now we are in the cooperate defect scenario where Alice gets 3 and Bob gets nothing. So yeah, that's it. And by the way, we also combined these games in some branching games. So what is the idea of a branching game? Let's look at it here. So if we go back, we showed The first normal prisoner dilemma is this one. Then we showed the prisoner dilemma with a commitment device, a non-extortive one in this case. And now we can combine these two. We can combine these two in this branching game that is basically says either we play traditional, we play the prisoner dilemma with a commitment device, or we play traditional prisoner's dilemma. So now we can use this in this other game where basically Alice has to decide which game she wants to play. So she can say, I want to play the prisoner dilemma with commitment, or I want to play the traditional prisoner dilemma. And this decision is observed here, and it's fed into the branching game. And the branching game will basically go to whatever branch has been chosen by Alice. And then, whatever branch is already defined up here. The important part when you define a branching game is that you have to provide strategies for all the possible branches. So you say, in this case, the strategy for Alice would be choose to play with the commitment device. Now, if we get in the commitment device game, she doesn't have to do anything, so she doesn't have to provide strategies. But if we go to the traditional dilemma game, she needs to provide the strategy, either cooperate or defect, and in that case, the best would be defect. Same thing, Bob needs to provide two strategies. One strategy is for the first branch, and the second strategy is for the second branch. Because again, Bob doesn't know a priori in which branch the game will end up being played. So he needs to be ready for all possible outcomes. And then again, in this case, we verified that between traditional prisoner dilemma and prisoner dilemma with a commitment device, Alice has more convenience in playing with a commitment device and in playing cooperative, and Bob to play cooperatively in this case. In the extortive scenario, it's actually the same. Like as long as the rate of extortion is kept low enough so that for Bob it's still more convenient to cooperate. If you bake all this into a branching game, then it turns out that Alice has an incentive to play the extorting game with respect to the traditional prisoner's dilemma with no commitment device whatsoever. Okay, so these are all the games that we implemented. And then basically we did something more. I don't know if probably I will just like glance through it. But the idea is that now we created a new player that we call a coordinator. And what is the point here? The point is both Alice and Bob now have to bribe the coordinator to pay a fee to the coordinator to get the right to use a commitment device. So what happens in this game that is a bit more involved is that both Alice and Bob have an incentive in front-running each other so that they can basically decide which commitment device to play, and then they can use this decision to extort the other player. So this whole thing is basically a very gradual way of showing where MEV comes from. So you have a game, you invent a commitment device, everything seems cool. Oh wait, the commitment device can be used to extort money to other people. Okay, let's insert a coordinator in the game to decide who goes first, and then you have front running emerging. Like the best strategy for this coordinator game is exactly front running the other player. And so yeah, this is completely public, and you can find it online. I can give you the link. You can find it on the 20 Squares GitHub page. And yeah, you can play with it, especially if you know a bit of Haskell. I think it's fairly quote unquote easy to play with. Yeah, that's everything I wanted to present regarding this software suite, and I hope that this gives you an idea of how, you know, game theoretic auditor works. Someone that does, yeah, spec audits and mechanism design audits works. We basically do these models and try to test some stuff. So yeah, if you have any questions or if you want to see some other stuff, just ask, and I'll be happy to answer.
So
Okay. Let me see. What do you mean by type of vulnerability precisely? So regarding the first question, which kind of problem do you report to clients? It's more like clients come to us with problems they want answers to. So for instance, there is this other project that we did for Manifold. Oh, okay, cool. I'll get to that in a second. So just to give you an idea of the kind of problems that we do try to solve, we had this work with Manifold Finance, and basically they wanted to, test, to deploy, to provide a service where you could pay for future gas prices. So their idea is, I reserve some block space now at current gas price, and 10 blocks from now or whatever, I get to submit a transaction, which I basically already paid for. And so Manifold was basically asking us in which kind of market conditions do people have an incentive to use this kind of future gas price mechanism. We modeled it, and obviously, there is a fee that you have to pay to use the mechanism. So if you assume that, in the future, price can swing in any direction with more or less equal probability, you model these as a Gaussian curve, basically centered over the current gas price. Then it turns out that people don't have any incentive to use this thing because, gas price tomorrow could be lower or could be higher with equal probability. So all things considered, I'm just paying an extra fee. But if your players are risk averse, then things change. So what it means to be risk averse, in a nutshell, imagine this. Someone says, hey, I can either give you $50 immediately, or you can play a game where basically, I extract a random number from 1 to 100, and I give you exactly that amount of dollars. So if you're risk neutral, you do not care at all between the two games. They are indifferent for you because they have the same expected value. In one case, you get 50. In the other case, you get a probabilistic result, but the average is 50. So it's the same. If you are risk loving, instead, you prefer the lottery, the game with extraction, because it's saying, yeah, I could lose more, but I could also gain more if the value that gets extracted is higher than 50. So it's like saying, for me, taking the risk is less important than being able to take the extra payoff. A risk-averse player would do the opposite. It would take the $50 with certainty, because basically, it would say, yeah, I could win more, but I could also lose more, and I want to hedge against that risk. So it turns out that using this future gas price reservation mechanism works well if both whoever uses the mechanism, the final user, and whoever provides the service are both risk averse. In this case, the user is hedging against gas price going up, and the service provider is hedging against gas price going down. And so we basically were able to, create very precise graphs where we could basically show, given some fees, how much risk averse buyer and seller must be to use the mechanism. And so that basically gave them a better idea of, in which market regime this thing would be profitable. Okay, I'll get to that in a second. So regarding the second question, like reentrancy, smart contract auditing and stuff like that. So it depends. Like, if we were to model smart contracts really like in open games, really verbatim and with all the details in place, then for sure, like re-entering would pop up as a profitable strategy. But basically, the kind of thing that we usually do is we take a mix of code and specs and we abstract stuff. So for instance, if you tell me, I have a cryptographic primitive that does blah, I will just assume that your cryptographic primitive works. It is not my job to test that, if your cryptographic primitive is badly implemented or stuff like that, because I'm working at the level of the mechanism. So assuming that your cryptography is good and that allows you to do what you'd say it allows you to do, then I can, do this, and that in my model. This is important because you understand that basically what we do goes hand in hand with traditional auditing. It's this thing doesn't replace traditional auditing in any possible way. You will always need traditional auditing services anyway. What we do is we just cover these, incentive design space that is basically left uncovered by traditional auditing, or is done in a way that it's, I don't want to say hand-wavy, but not with the right tools, because not with the tools that are really implemented for this job. Okay, so second question, could you say more about the detection of unstable games? Okay, so I would guess that by unstable games, you mean games where you have strategies where you don't have an equilibrium, basically, right? So where you can circle around. So, okay. Basically, there are three things that you can do with this open games engine. The first one is simulations. So you just provide a strategy and the engine will tell you the payoffs, will tell you how much all players get with the strategy profile that has been specified. The second thing you can do is equilibrium checking. So you give a strategic profile and you ask to the open games engine, hey, is this strategy profile an equilibrium? What the engine will do, this is what we tested in the demo before, it will try all the possible deviations and it will highlight if some deviation is profitable for some player according to whatever notion of equilibrium you want to use. We assume Nash almost invariably, but other choices are possible. And then you can do equilibrium finding. Equilibrium finding means I just define the boundaries of the strategy space and then you explore it. So for instance, in the prisoner dilemma game, we see that the strategy space into traditional prisoner dilemma is just 4 things, because the strategy space for Alice is 2 possible operations. The strategy space for Bob is 2 possible operations. So there are 2 times 2, 4 possible things to do. And you can basically brute force it and see what strategy is an equilibrium, if there is one. Obviously, when you go to mixed strategies or to more complex games, then it becomes much harder because your strategies, your action space may be infinite, may be continuous, right? If you do probabilistic, it's not anymore playing cooperate or defect, it's playing every possible probability combination, between cooperate and defect, and that's as many as the real numbers. So long story short, this is something that came up a lot also in discussions with flashbots and stuff like that. Usually, equilibrium searching in full generality is not a good idea. It's very computationally heavy. It is a theorem in traditional game theory that, that is a non-tractable problem computationally, and you can't go around theorems. So it would be the same in open games. The good thing is that usually when the client comes to you with a mechanism, they have a pretty good notion of what they think is the equilibrium behavior. So what I can do is I can take them at face. Yeah, probably is undecidable. I mean, yeah, you could be right. It's just like nightmarish. But basically, the client comes to you with already a notion of, in their mind, what is that they think should happen, and then we can implement that and check if they're right or wrong. So for instance, in the case of manifold finance, they had already an idea that, for the system to be profitable and, for users to be incentivized to use it, they had to be risk averse, at least to some degree. And so we basically verified that that's true. Without risk aversity, there's no equilibrium. With risk aversity, there is equilibrium. But especially, in auction design, order flow auctions design, it's basically turning out that simulations are even more important than equilibrium checking. Sometimes you don't care at all about equilibrium. You just, want to simulate a given strategy and have an idea on how much you will make with that strategy. So basically, all these things are useful in a way or another. How complicated the process is, how complicated the thing is. In general, I mean, rarely we exceeded 3 weeks of work for various reasons. Sometimes the client is satisfied with just a toy model. Sometimes they want to, simulate or model just a small component of their ecosystem. It really depends. To be honest, for us, the most difficult part is not writing the model. Is the most time-consuming part is understanding what the client wants to do. Because again, remember that we can work also when not a single line of code is being written yet. We can basically, test on specifications. So in traditional auditing, usually you get a smart contract in or some code in, and you can basically audit the code. And you know what the code does because you can read the code. In our case, it's way more complicated because sometimes there's no code. There's just like a poorly written spec, or even not that sometimes. And so there is this whole process of brainstorming with the client and trying to really understand what they want. And that can be very fast or really, really long, depending on who's on the other side, basically. But yeah, in general, I would say 2, 3 weeks, 5 weeks max up to now. But also, with this kind of system where you can reuse things, basically, it's nice because when the client is satisfied, they keep calling you. And so as they implement new things or they extend their system, we extend the model accordingly. And that is something that we can do fairly quickly, given that, we can reuse model material, basically. So, yeah. Okay, I've heard about some economic simulations that use agents. No, agent-based modeling is something a bit different, I would say. Let me see if I can explain to you very quickly. Modeling. So yeah, yeah, no, I wouldn't say that it's the same. There are, by the way, agent-based modeling is a large field, but it's not the same of what we usually do. I think that probably the similarities are in the fact that our games allow for Bayesian reasoning, and that is something that sometimes you see in agent-based modeling. But for instance, all the stuff about Monte Carlo methods and et cetera, that is not something that will do. So no, they are not exactly the same. Also, I think the difference becomes more stark when you start looking at, for instance, equilibria in repeated games. So one thing that we can do is also repeated games. Those are a bit more complicated, so I won't go through them at the moment. But the idea of a repeated game is, yeah, as the name, like, okay, the general idea that we use is the one of Markov game. Markov game means that you have a game, you do something, and depending on what you do on this game, you decide what game to play next. A very simple example of a Markov game would be modeling a Japanese auction, for instance. So Japanese auctions work like this. All the bidders are in a room, and there is, basically a display that shows a price, and this price increments every 5 seconds by a fixed quantity. Basically, if the price is still good for you, you stay in the room. If the price is not good enough, is too high for you, you leave the room and you cannot enter again. As soon as there is only one person left in the room, that person wins the auction at the displayed price. Now, the way you implement this is as a Markov game, where at each stage you see the price, and every agent can either leave or stay in the room. And basically, depending on how many people play stay and how many people play leave, you determine the next game. If more, if basically there is still someone in the room, the next game will be the same game with a slightly higher price. If no one is left in the room, then the following game will be the end game, where the payoffs are calculated and you basically assign the winner of the bid. And in agent-based modeling, you basically simulate this kind of things. Well, in our case, yeah, you can basically just test for equilibrium. I would say that another stark difference with agent-based modeling is that we depend way less on pre-existing data. So, for instance, one question that we get asked all the time is, okay, how is what you do different from what Gauntlet does? By the way, we are friends with Gauntlet, super nice people, but I would say that the main difference is that their approach is heavily based on ML techniques and on using, previous data. Like, they specialize in risk management, and they basically take statistical data of your protocol that they fetch in a plethora of ways and run simulations based on this data. In our case, we can integrate that data in our models, but the model exists a priori. So what that means is that we can basically come much earlier in the product development cycle. Imagine that you have a new financial primitive that you didn't implement yet, is not released, and so you don't have any data points. At that point, doing agent-based modeling and all this kind of stuff becomes really hard because you don't have data. we can still do a model and basically stress test it. And afterwards, when the data gets released, when the protocol or the primitive gets released and you start accumulating data points, then you can integrate those data points in the model. Obviously, when you don't have any data, there is always a risk that, you know, what you're going to do will be bullshit, because maybe, I mean, you have to be very clear on the assumptions that you're doing, clearly, that you're making. So if you make bullshit assumptions, you will get a bullshit model. And no amount of mathematics can save you from this. So yeah, but I would say those are the main differences. By the way, I forgot to ask. I don't know usually how long are these sessions, if they are 1 hour or 2 hours. I really don't know. So okay. Cheers. Yeah, if there are some other questions, either here or you can reach me out on Twitter or via email. My email is just like fab or Fabrizio at 20squares.xyz. Or yeah, I mean, yeah, I don't know, whatever. If you want, reach out and I'll answer your questions. I will write here my email address. This is my email address. You can also mail at info if you have a more general question. And I also want to give you the link to this repo. So the link to this repo that is fully documented and stuff would be here. This one. And if you want to take a closer look at the Open Games engine itself, I will also give you this one. So this is the GitHub repo of the Open Games engine. And this is a thing, I promise. This is an archive paper that basically details the underlying theory. It's basically all category theory. That is what we do in this guys. But yeah, those are, I would say, the main sources. We at 20 Squares have no social media whatsoever. Like, we can't be bothered, so I can't give you any Twitter handle or Telegram handle for that. I hope email is enough. Yeah, that's it. Thank you.